When you think about the technology of today and the innovation in the 20th century that got us here, you might think of NASA, maybe the Manhattan Project, or about Silicon Valley developing microchips. But which of these legendary organizations did the most innovation? The answer is Bell Labs.
The responsibility of Bell Laboratories is to provide the science and technology to turn AT&T's vision into reality.
They likely produced more discoveries and inventions than any other organization in the 20th century and enabled AT&T to become a company so large that the US government had to break them up in 1984. This is the story of that innovation, and it's the story of Bell Labs. In the past few months of filming S3, I felt like something was missing. The reason I make this show is to study the art and science of innovation. And not only that, but to try and convince you that if you want, you can have a part in it. But it feels wrong to only focus on the companies of today and totally ignore big and in many cases underrated stories of innovation in the past. This is our first ever historic S3, meaning that the story we'll tell isn't about a company that's trying to build the future today, but is instead about a team of people who innovated in the past to bring us to where we are in the present. So why Bell Labs? At the peak of its reputation in the late 1960s, Bell Labs employed about 15,000 people, including some 1,200 PhDs. Its ranks included the world's most brilliant and eccentric men and women. In a time before Google, the lab sufficed as the country's intellectual utopia. As it happens, the past offers the example of one seemingly wicked problem that was overcome by an innovative effort that rivals the Apollo program and the Manhattan Project in size, scope, expense, and duration. Before reading this book, I didn't really know much about Bell Labs. I had heard about the Manhattan Project, I'd seen the Christopher Nolan movie, and I've seen all the movies and media about the Apollo program. But the Idea Factory by John Gertner kind of uncovered this world of innovation that I had never heard of, despite being someone who tells a lot of stories about people who do innovation. It's easily one of my favorite things I've read in 2024. So if you finish this video and you like what you hear here, you should definitely buy and read this book. Okay, now let's get on to the story of Bell Labs. The story of Bell Labs starts almost 100 years ago in a 400,000 square foot building in New Jersey. But to set the stage for that, 40 years prior, AT&T was founded by Alexander Graham Bell, the inventor of the telephone. By this point, AT&T had taken off and was basically the leader in most phone calls going on in the United States. But competition was beginning to build up. Other people were building phone networks and trying to come for the throne in the kingdom that Alexander had built. But in 1907, Theodore Vail took over leadership at AT&T, and he had a vision about the future of what their business could look like, that he and his infamous PR arm coined as one policy, one system, universal service. Universal service was this sweeping vision, something ridiculous that nobody had dared to dream before, a total and complete telecommunication system that could connect everyone, everywhere, under one system and one policy. Today, that sounds sort of obvious, but back then it was crazy. The Vail strategy, in short, would measure the company's progress in decades instead of years. To pull off this crazy dream and ambition, they'd need to build it. And not only that, they need to discover the material science, engineering, and physics to do that. They'd need to invent it. Existing technology simply couldn't support the kind of long-distance, reliable communication they envisioned. At that time, you could basically make a call to halfway across the country. There was no way to make a phone call from New York to California. But in 1915, during the International Exposition in San Francisco, AT&T showcased a groundbreaking achievement, the first transcontinental telephone call. Alexander Graham Bell hopped back on the phone in New York and spoke to his former assistant, Thomas Watson, in San Francisco. This feat required an immense amount of labor. This continental link was strung from the east to the west coast with over 130,000 wood poles. This wasn't just a demonstration of technological prowess. It was a symbolic moment that proved their vision was attainable. It was an idea that technology could unlock new business potential. And that led to the creation of Bell Labs. Vail brought in Frank Jewett, a brilliant engineer who became the first president of Bell Labs. And while Jewett laid the groundwork, it was really Mervyn Kelly who ran the show in later years. He fostered an environment where creativity and collaboration thrived. So the founding team got set up in 1925 with a starter budget of $12 million a year, or $220 million in today's cash. This is an insane amount of money and something that could have only been possible from the monopoly that was AT&T. Bell Labs was structured to prioritize long-term thinking. This was a big thing that Theodore Vail pushed. But this wasn't for altruism. Theodore Vail believed that technology, over the long run, could provide immense business value to AT&T. Researchers were given remarkable freedom to pursue almost any line of inquiry, as long as they could justify that it might one day contribute to building the system. This wasn't a place bogged down by immediate profit margins or quarterly reports. It was a crucible for innovation, where the only limit was imagination and research. And right down the street was Western Electric, AT&T's manufacturing powerhouse. Bell Labs would come up with an idea, and Western Electric would build it. This seamless integration between theoretical research and practical application was a game changer. Now let's meet the young Turks, the brilliant minds who became the beating heart of Bell Labs. First up, we have William Shockley, a theoretical physicist with an uncanny ability to see where technology was headed. Later in life, Shockley had some not-so-scientific views. Yeah, that's pretty bad. We'll stick to just talking about his physics work. Then there's John Bardeen, the quiet genius. Despite his reserved demeanor, his contributions were monumental. And fun fact, he's the only person to have won the Nobel Prize in Physics twice for entirely different breakthroughs. Then there's Walter Brattain, the experimental extraordinaire. He had a knack for translating complex theories into tangible experiments. Colleagues joked that he could build anything with a piece of wire and some chewing gum. And we can't forget Claude Shannon, the mathematician and electrical engineer who laid the foundations of information theory. In a single video, we can't mention everyone who is a critical part of Bell Labs' magic. And again, go read the book. They're talked about a ton in here. The vibe at Bell Labs was electric. They published their own journal, shared insights, and had sparking discussions where they talked about deep topics that weren't even a thing, like solid-state physics. Let's talk about one of their first big innovations, the vacuum tube. In 1912, a crucial advancement in vacuum tube technology happened almost by accident. Around 1912, Harold Arnold was trying to improve the audio, an analog amplifier brought to Bell Labs in 1912. Through trial and error, Arnold discovered that in high vacuum, and with the right materials, you could greatly improve the audion's efficiency. They were called vacuum tubes. This serendipitous discovery allowed for better amplification of signals, paving the way for long-distance telephone calls and radio broadcasts. Telly called the tubes miracle devices that would usher in a great age of electronic communications, but he knew better than anyone how difficult they were to make. A few decades later, after AT&T had begun to proliferate vacuum tubes all across the US, William Shockley was having some interesting ideas relating to semiconductors. Shockley had concluded by then that a certain class of materials known as semiconductors, so named because they are neither good conductors of electricity nor good insulators of electricity, but somewhere in between, might be an ideal solid replacement for tubes. The possibilities of using semiconductors was enormous, but then the war came. World War II shifted the global landscape, and Bell Labs was no exception. But that didn't stop them from innovating. Bell Labs led over 1,000 projects for the US military during World War II. They applied their expertise to develop radar, encryption devices, and other technologies critical to national security. When we think about the technological feats that contributed to the Allied victory in World War II, the atomic bomb often takes center stage. But in reality, it was radar that truly turned the tide of the war. It's often said that the atomic bomb ended the war, but that radar won it. To put this into perspective, the United States spent about $3 billion on radar development during the war, compared to a measly $2 billion on the Manhattan Project. So how does radar work, and why was it such a big deal? Radar, which stands for radio detection and ranging, is a system that uses electromagnetic waves to identify the distance, speed, and direction of objects. It sends out radio waves that bounce off of objects and return to the source, allowing the system to calculate an object's position and movement. It meant that for the first time in warfare, armies could see beyond the horizon, detect incoming threats in any weather, and coordinate their defenses with unprecedented accuracy. Bell Labs was instrumental in the radar revolution during what was often called the physicists' war. The war effort led to explosive growth at Bell Labs. At the beginning of the war, there were 4,600. By the end, they had 9,000 employees. As the war drew to a close, Bell Labs didn't slow down. In fact, Mervyn Kelly had a post-war reorganization plan ready to go the moment peace was declared. Post-war Bell Labs went on what can only be described as a spending spree. Kelly, Buckley, and Jewett were of the mind that Bell Labs would soon become the largest and most advanced research organization in the world. For the past 5 years, in between all of his wartime work, Kelly had devoted large blocks of time to orchestrating the construction of an immense complex of buildings in the wooded hills of New Jersey. With a price tag of $4 million, the new building was not conceived as an ordinary laboratory. All the buildings have been connected so as to avoid fixed geographical delineation between departments and to encourage free interchange and close contact among them. The physicists and chemists and mathematicians were not meant to avoid one another, and the research people were not meant to evade the development people. By intention, everyone would be in one another's way. Members of the technical staff would often have both laboratories and small offices, but they might be in different corridors, making it necessary to walk between the two, and all but assuring a chance encounter with a colleague along the way. This period marked the beginning of an unprecedented era of innovation at Bell Labs. In 1947, Bell Labs scientists John Bardeen, Walter Brattain, and William Shockley developed the first working transistor, a small device made from semiconductor materials like silicon and germanium. This tiny component could amplify and switch electronic signals, effectively replacing the bulky and unreliable vacuum tubes of the time. The transistor was more than just a technical achievement. It was a cornerstone of the electronic age. It led directly to the development of virtually all modern electronics, from computers and smartphones to medical equipment and satellites. But there's more to the story. John Bardeen didn't stop with the transistor. He went on to co-develop BCS theory, or superconductivity, which explained how certain materials can conduct electricity without resistance at extremely low temperatures. One of the biggest innovations came in 1954, when Bell Labs scientists Darrell Chapin, Calvin Fuller, and Gerald Pearson developed the first practical silicon solar cell. This device could convert sunlight directly into electricity with an efficiency of 6%, which was a significant leap at the time. This invention marked the birth of photovoltaics, paving the way for solar panels that power homes, satellites, and spacecraft today. Bell Labs was also at the forefront of laser technology. In 1958, Arthur Shallow and Charles Townes published a seminal paper outlining the principles of the laser, which stands for light amplification by stimulated emission of radiation. During this time, Bell Labs wasn't only looking at the ground, they set their sights on the stars. In 1960, they launched Echo 1, a passive communication satellite, meaning that you would just shoot RF signals up at it and they would bounce it back to you. It was a bold experiment that proved satellite communication was feasible. Building on this success, in 1962, Bell Labs introduced Telstar 1, the world's first active communication satellite. Unlike Echo, Telstar could amplify signals before retransmitting them back to Earth. This allowed for the first live transatlantic television broadcast. Sometimes, the most profound discoveries happen by accident. In 1964, Bell Labs astronomers were working on a project involving satellites using a giant horn antenna. They kept encountering a persistent background noise that they couldn't eliminate no matter what they tried, even after evicting some pigeons nesting in the antenna. They had stumbled upon the cosmic microwave background radiation of the universe. This is the afterglow of the Big Bang Theory and is sort of the bedrock of a lot of cosmology research done today. The innovation didn't stop there. In 1969, William Boyle and George E. Smith invented the charge-coupled device, or the CCD. This technology allowed for the electronic capturing of light images, effectively replacing traditional photographic film. CCDs became the heart of digital cameras, medical imaging devices, and telescopes. By the late 1960s, Bell Labs had reached its zenith. The institution boasted over 15,000 employees, including 1,200 PhDs. It was a melting pot of intellect and creativity, unparalleled in scope and impact. Imagine walking through the halls of Bell Labs during this era. To get from one side to the other, it was intentionally designed again so you cross paths with other people. You might pass a physicist pondering the mysteries of the universe, or an engineer designing cutting-edge communication systems, or a mathematician laying the groundwork for computer theory and writing a unicycle, all under one roof. The innovation from Bell Labs didn't just stay within the confines of the company, they rippled outward, influencing industries and sparking new fields of study entirely. The transistor led to the development of microchips and the entire semiconductor industry as we know it today. Possibly one of the most significant contributions and one of the most remarkable individuals to emerge from Bell Labs was Claude Shannon, known today as the father of information theory. Shannon's work laid the foundational principles that underpin our digital age. But don't take it from me. Here's a clip from a secret project I'm working on from the co-founder of Neuralink, who's now working on his own company, Science, on the impact of Claude Shannon in information theory.
So information theory really got its start in the 1940s. Claude Shannon was working at Bell Labs. He was working for a telecom, and they wanted to know, they were going from analog phone lines, so how do we scale this? And so the problem that he was looking at is if you receive a signal in one place, how do you transmit that over a wire to recover the signal somewhere else? And how do you do this in a way that is not just, as your wire gets longer, it gets noisier and it gets harder to hear? The idea of digital coding is not about electronics or CPUs. It's about taking these analog continuous, noisy, real-world systems and building encoding schemes that allow you to perfectly encode information that is always recoverable. And so Claude Shannon was thinking about this at Bell Labs. He ended up writing a paper called A Mathematical Theory of Communication. He was looking at, like, if you look at the statistics of English, you've got letters, and you can randomly sample one of the 26 letters of the alphabet. This looks like gibberish. But if you look at sampling letters based on one prior letter, so E is more often after A or after B or whatever, then you get something with a little more structure. Or if you look at sampling based on 2 letters, and these are called n-grams for 1 or 2 or 3 grams, you can calculate the statistics of how often do these letters follow each other. And maybe now you split by words. Now, instead of sampling out letters, you're sampling out words from the dictionary, and you're looking at what words tend to appear after other words. And so as you go out to longer structure, you get this emergent structure, which encodes something about like the statistics of the language. So what is, like, how do you represent all of this? Like, what are we dealing with here? The thing that's fundamental underneath. And he came to this idea of the bit. And like, what is a bit? The definition he offered was a difference that makes a difference. This is an idea which is so general as to be kind of tough to reason about when you're new to it. And I think that's one of the reasons that it's had such staying power, because it is such a profoundly general idea that it kind of has lives in all these different areas. And this all came down from how do we build fault-tolerant encoding schemes that allow us to span across the country with telephone wires.
Information theory was discovered and predicted to be monumental long before its full potential was realized. This simple idea that any sort of information, small, big, or massively complex, could be encoded as a single binary value of a 0 or a 1 was groundbreaking. He showed how information can be quantified, transmitted efficiently, and encoded to reduce errors even over noisy communication channels, something previously thought impossible. As a result of information theory, Bell Labs developed Unix, an operating system initially designed for internal use to replace the analog process of telecommunications switching. It was created by Ken Thompson and Dennis Ritchie, who were looking for a platform to run the game Space Travel, believe it or not. From Unix came the C programming language, developed by Dennis Ritchie in 1972. C was designed to be a high-level language with low-level capabilities, allowing programmers to write efficient code with direct access to the hardware. Building on C, Bjorn Stroustrup at Bell Labs later developed C++. C and C++ became the backbone of modern software development. Unix itself became Linux, and Mac OS is built on Unix 3. All of this innovation didn't happen in a vacuum. It was underpinned by the unique environment at Bell Labs, a place fueled by the financial backing of a monopoly. That same monopoly would be its downfall. AT&T, the parent company of Bell Labs, held a monopoly over the entire telephone services in the United States for much of the 20th century. There was growing concern that AT&T's monopoly stifled competition and innovation in the telecommunications industry. Over the years, the government intervened many times, leading to various legal battles and restructurings. The most significant change came in 1984, when the US Department of Justice mandated the breakup of AT&T in an antitrust settlement. This led to the divestiture of AT&T's local telephone operations, which were split into 7 independent regional Bell operating companies, often referred to as the Baby Bells. This breakup marked the end of an era for Bell Labs. The lab itself was split as well, with parts of it remaining with AT&T and others becoming part of newly formed companies. The monopoly that had funded and fostered such a prolific period of innovation was no more. There's a certain irony here. The innovations that Bell Labs produced, especially in electronics and computing, helped create the new industries and competitors that ultimately pressured AT&T's monopoly status. By inventing technologies that would become ubiquitous, they sowed the seeds for a more competitive and diversified telecommunications landscape. In many ways, the monopoly enabled more innovation from a single lab than the world had ever seen prior. I got so excited about the research for this video that I tweeted a bunch of pictures of Bell Labs, just sort of awestruck with their innovation. And a lot of people in the replies had one question: who are the Bell Labs of today? Well, oddly enough, on the same day that I tweeted that, DeepMind from Google released a significant update to AlphaFold, releasing AlphaFold 3. A groundbreaking AI system that predicts protein folding, which is an immensely complicated thing to do. I think some potential candidates for very profitable cash engines that can fund research organizations might be Stripe, funding Arc Institute, There's of course SpaceX as a total organization, which is developing Starlink as its own cash engine to fund its research and exploration of Mars. I think these are some contemporary examples of organizations investing heavily in long-term, high-risk reward projects, but are they the Bell Labs of today? This brings me to the dichotomy between startups and research labs in our current landscape. On the one hand, you need money, and commercial instinct often drives innovation. But the kind of groundbreaking work that happened at Bell Labs exists well outside of the typical venture capital window of interest. Bell Labs was all about the long game, and you couldn't have had that without a massive cash engine and a monopoly. I think a good note to land on is just how important the individual is in innovation. Bell Labs at its height was 15,000 people with 1,200 PhDs, but there were a key few people that had some of the biggest breakthroughs and discoveries. There are examples of this outside of Bell Labs too. Think of Bill Knudsen, who was instrumental in getting the US manufacturing base ripping during World War II, or J. Robert Oppenheimer and General Leslie Groves in the Manhattan Project, and of course, Mervyn Kelly and the Young Turks at Bell Labs. Kelly fostered an environment where long-term thinking wasn't just encouraged, but was ingrained in the very fabric of the lab. His leadership style was pivotal in making Bell Labs the powerhouse of innovation it was. I think that's the thing that I'm most obsessed about with in studying success cases like Bell Labs or the companies that are innovating and pushing the bounds today, is the impact that single people can have in our grand story of innovation. The reason that I film S3 is to try to get an inside peek to what super ambitious and innovative teams are up to today before they go on and do the next big thing. We have some pretty exciting episodes coming up here in S3 where I think some of the innovation going on feels like some of the early days of Bell Labs. Thank you for watching this new style of S3. Let us know what you think. It's kind of this new hosted historical format. I really enjoy exploring these deep dives into the stories and behind these technological revolutions, and I hope you do too. If you've got any cool lore or stories about Bell Labs that we didn't cover, or any thoughts that you want to share after watching this, like, we'd love to hear them in the comments. I'm sure that some people have like friends or family that worked there. It'd be cool to hear your take. And before I go, I'm going to close off with a passage near the very end of the book, The Idea Factory by John Gertner, that this video is heavily based on. Do not watch this part if you don't want to hear the very ending of this book. Pierce hoped privately that the work he and his colleagues did would someday be broadly recognized. What mementos will our heirs have of our romantic present to tell them that men created the things which they take for granted? He feared that any memories of the makers would perish too. I'm afraid that there will be little tangible left in a later age to remind our heirs that we were men rather than cogs in a machine. Thanks for watching. Hope you enjoyed this, and until next week, keep on building the future.